Welcome back, everyone. Thank you so much for your patience, and thank you for being with us through Zoom or YouTube. To conclude today's set of lectures, we welcome Dr. Boris Escalante Ramirez, professor at UNAM's Faculty of Engineering and a pioneer in biomedical image processing. His lecture on vision models will show us how computers see in medical context. Please join me in welcoming Dr. Boris Escalante Ramirez.
Well, thank you very much for inviting me to participate in this school, and thank you to Dr. Thomas Desarno for visit, and Dr. Tim Kakprowski. I hope I pronounced your name okay. Thank you very much for being here. So the idea of this session is to talk a bit about vision models and why they are important for the work we do in image analysis. So first of all, who I am, I belong to two places. One is the LAPI, the Advanced Laboratory of Image Processing, which is in this School of Engineering, where we do research just on this area, digital image processing, computer vision, machine learning, with a strong emphasis on medical images. And on the other hand, I'm the general coordinator of the Center for Advanced Computing Studies of UNAM, which coordinates projects that have to do with research, education, and dissemination. Okay, so why I'm going to try to motivate this talk why vision models are important for this topic. David Marr, who is considered the father of computer vision, says or said one time, vision goal is to produce useful description of the outside world free of irrelevant information. That's what we all do when we're looking at visual information, trying to discriminate the important features of images that we need to do a certain task like image recognition, etc., etc. On the other side, Ian Goodfellow, more recently, who is one of the fathers of deep learning, made this reflection. Computers nowadays can do astonishing things like beating the best chess player, but on the other hand, they take hard time trying to solve tasks that are easy for us. For instance, recognizing a person, which is something very easy for us humans. Computers can do it. They can do it now recently, but it took a hard time for them. And that's this challenge that we have to do now. Try to do scene understanding, try to interpret, try to extract semantic information. No? That's something that we humans do very easily, but it's very difficult for computers. Okay, so what are the applications? I think during this school, many applications have been discussed. Number of things that can be done in computer vision. For instance, optic flow segmentation that just recently talked about with Dr. Jimena Alvarez, fusion, recognition. And on the side of applications, well, there are a lot of applications. We are very much focused this school on medical applications. Well, one of the most important applications is computer-aided diagnosis that have to do with all these tasks that are here, optic flow, fusion, segmentation. No? Okay, now, I want to stress in this talk the importance that human perception has on image analysis. And to start with, I'd like to mention the work by Hubble and friends and colleagues who, from about 1950, made important discoveries of how our human system work, our visual system work, especially in the early stages of human vision. So he was successful in modeling some of the more important simple cells of human visual perception that start working at the retina. Yeah, so at the retina we already have some important image processing, image analysis tasks, and also in the first layers of the visual cortex. And what I want to stress here is that the models that they found out are mathematical models that can be modeled again as a derivative of Gaussians. No, if it's not that we have derivative of Gaussians in our systems, but the cells can be very well modeled as derivative of Gaussians. Okay, now the funny thing is that although these people did this research in the 1950s, we took a long time to absorb these discoveries into image processing. And the first people who took advantage of that knowledge, were painters. For instance, Salvador Dali, who painted this image with a lot of detail. It's like a 3-meter high painting in which we have details. We have here Gala, and we have Gala looking at the sea through a window, and we see a lot of details. And what Salvador did is he really studied the works of Hubble to paint this painting. And what he intended is that people go back and see the painting from a larger distance. That is what we are doing here. And if you see, when we put the painting farther away from us, we don't perceive anymore the details of the original image, but we perceive what? What do we see here? Somebody here? My students, where are my students? Right, Abraham Lincoln, right? So Abraham Lincoln is what? No? So this is a task that if we ask a computer to find out the edges of Abraham Lincoln, it would be very difficult if we processed the image at high resolution. What we have to do is process the image at low resolution, and then the large objects come by itself. No, it's a very simple. Thomas. Right. Yeah. So people, if you have this one, and you close, as Thomas says, you try to look at the image through the eyelashes, you're actually doing a low pass filtering, and then you get the image, So that very simple knowledge of how to do multi-resolution analysis was aware to people who are doing image processing much later, But this guy already knew that from 1975. There's another example which is similar. This is Georges Seurat, French painter who was an impressionist with a specific technique which is called, I know in English, is puntillismo. He just paints points, dots of different colors. And if you look at the image from far away, you see this, and you can see, for instance, this person, you can find the contours, the edges of the person. But if you look at the painting from very close, what you see is this, just a bunch of dots, who are not even connected with edges. So what we have to do is go far away, and then the edges connect one with each other, and then contours edges start appearing. And another thing is that the phenomenon of color fusion works a lot here because dots of different color merge together, and when we find different colors. Right? And this guy was in 1888, now much before than we started working with vision models. So we started working with these models around the 80s. That's when we realized that that knowing about the human visual system was useful to do image processing. Now it sounds very logical, but we realized that in those times. No? So many models starting to arise as models of human visual system applied for image and computer image analysis. No? Okay, a more technical example of the need to know visual perception for image, in this case, image visualization of images is, for instance, these. These are the first displays that we had, the first LCD displays that we have. No, they started appearing around 1990, and this is how they look at the beginning. And they were very expensive. They were very small, and people said, well, if they're expensive and small, why am I going to spend so much money in buying one of those things? Because, as you see, there is a pattern, a vertical pattern, which is very annoying from the perceptual point of view. And if we look at why is this pattern appearing? So this is a close caption of a close look of the eye. Yeah, we see that the visual patterns arises because there are vertical patterns of the pixels that are the red, the green, blue pixels ordered in vertical position, and they produce this very annoying view of the image. No? So one possible way to solve this is this. No, so this looks much better. And when we see how this image is how this problem was solved, this is the solution. No? What they did is they designed much smaller pixels that produce less annoying pattern. No? But at that time, this was not possible. No? I mean, the technology was not possible. It was not able to do smaller pixels. And if in case that it would be possible, it would be much more expensive. No, there are at least 4 more elements here than here. No? So this was not a practical solution. So what they did is this, and if you compare the image, the 3 images, no doubt this is the best one. But after this one, we have this one. Yeah, as the second best image. Is in subjective experiments, it came out that this was almost as good as this one. And when we ask how they did this is the solution they did. So what they did, they just, I don't know if you see it, they just shifted the pair lines of the display. They shifted half a period. That's all they did here. You see, they every second row was shifted to half the period. So the number of elements of this display is the same one as this display. So it doesn't cost more money. It's as expensive as the original one. And the subjective quality, which is the important one, is as good as this one, or almost as good as this one. And this is explained in terms of visual perception. What happens is that we humans are able to see much better vertical and horizontal patterns. And if we have a diagonal pattern, we can't see it very well. So it doesn't disturb very much because the let's say annoying pattern doesn't have a vertical or horizontal direction. And that's one possible explanation why we like more this image than this one. Because there's no other objective measure that you can extract from from this image that shows that this one is better than this was. In terms of information quantity is the same one. Then for signal to noise ratio, whatever you want, you won't find an objective measure that demonstrates that this one is better than this one. It's just a subjective impression. Okay, so, well, this is another example. This is the well-known Lena, which is now banned from experimentation, but we are making an exception now, and we're still using it. So an experiment we are trying to do with this one is what you see here. You see what did I do? I just added noise. Yeah, you see the difference between this one and this one. Yeah, it's the same image with added noise, and one of the most difficult tasks in image processing is to remove noise. Yeah. So if people who are familiar with signal processing know what is the best linear filter that there is, does anyone know what is the best linear filter that there is in terms of minimizing the mean error square because between the restored image and the original one? Yeah, there's a very well-known filter called the Wiener filter. No, that's the best linear filter that you can find with the criterion of minimizing the minimum square error between the original image and the restored image. And this is the result of the Wiener filter. But if you ask a general audience that doesn't know anything about Wiener filter, and if you just sit them like you are here in the auditorium and ask a simple question, which one of the two images prefer? Which one do you prefer? Which one do you prefer, people? Just forget about what I said about Wiener filter, and this is the best filter. You just arrived here and sat down, and I'm asking you, what's the best image? What image do you like the most? The one at the left or the right? Which
The
one?
one in the left.
Okay, left. Who is for left? Left. Okay. And who is for right? Right. Very few people. Okay, that sounds logical. So, and we ask people, why did you prefer the left one? Why do you prefer the left one? Contours, okay. No? The details of the image are better seen here because it is sharper. Yeah, the one at the right is blurred, and the one at the left is sharp. Yeah. And you can ask people, I can ask you, why do you like, I can tell you, I can argue, but I spent many months of my life building the Wiener filter, and it cost a lot of time for me. Why do you discard this one? What are you going to tell them? I don't care about the minimum square error. I care about human perception, and in human perception, quality, the most important thing is sharpness. Yeah. And the second most important thing is how annoying noise is. So sharpness is more important than noise. That's why we like more this one. No? So it doesn't mean that Wiener filter is useless. We use it both in an adaptive way so that it doesn't blur important features. But what are those important features? Lines, edges, and those kind of things. Okay. So this is just a motivation to, I'm going to skip this one, to argue why image representation models are important, and they need to take into account visual perception properties. No? There are a number of models that could be used and have been used to model image representation. For instance, we all know Fourier, cosine transform, Cajun-Loew, wavelets. Yeah, there are a lot of transforms that have been used. For instance, wavelets is a very widely used model. They have very nice properties like good space frequency localization, they are optimal subsample, they have no redundancy, and they have been very successful in compression. For instance, JPEG 2000 is based on wavelets, but also has disadvantages. It's no shift invariant. If I shift one pixel my image, I won't have the same representation. It has often non-regular waveforms, ringing, a lot of ringing, and that's very little, that has of little importance in terms of visual perception. It's non-redundant, I said before that it was an advantage to be redundant, but it's also a disadvantage because if I want to solve problems of redundancy, of reconstruction, I need redundancy. So to do image reconstruction, I need redundancy. So wavelets are not that good for image reconstruction. And there are many things. You have to take many wavelet coefficients to make a good reconstruction of important patterns for vision perception, just like an edge line, no? Just a simple pattern, a primitive pattern like edge line, which is very important in terms of visual perception, is very difficult to reconstruct or to represent with wavelets because you have to use too many coefficients, etc., etc. So what people did is go and look for other kinds of transforms that have to do with visual perception. And there are a couple of them. Gabor, which is, I'm going to talk about Gabor later, cortex, which is kind of representation of how we perceive things at the cortical level, and the one that we use that is the Hermite transform. I want to stress, or I want to ask you to remember that these cells of the principal cells of human perception at early stages can be modeled, as I said before, as derivative of Gaussians. And these two, Hermite and Gabor, are very good models of those cells. Okay, so these are the Gabor functions. They are very good. They are the one used for iris recognition. Yeah, the first algorithm for iris recognition was based on Gabor functions. They are very good. They are very good models of simple cells in visual cortex. They have small disadvantage. They are not orthogonal, so I cannot reconstruct an image once I analyze the image with Gabor. No? And the other one is the Hermite transform. This is the one that we use. And it's good because it has several advantages. First of all, it's based on the model of Gaussian derivatives, which I said are very important for visual perception. And these are the kind of basic functions that we use in the Hermite transform. And when we convolve these functions with an image, what I get is this kind of things, that as you see, the information that provides is just what I need, is edges, is lines, is those important features of images that we all need to make more complex tasks. Okay. So so these are the advantages, Gaussian derivatives. It can be used for multi-resolution analysis. The last rotation is very important. I'm going to talk about that later. It's redundant, which is useful for image reconstruction, and it's shift invariant, and it has a fast algorithm, which lowers the complexity. Which lowers the complexity to n log n. No? Okay. What's the definition of this transform? First of all, I'm going to show it here with a one-dimensional signal. Then we extrapolate to 2 dimensions. So we have here a one-dimension signal. The first thing that we do is to localize the image. How do we localize it? Multiplying the signal with a Gaussian window. Why is important Gaussian windows? It's the kind of things that we have in our system. We have something called the receptive fields, and the receptive fields have a Gaussian shape, no? A Gaussian-like shape. Once we localize the signal with many Gaussian windows, what we do is do an image, a polynomial expansion. So the piece of the signal within the window is going to be expanded in terms of a set of orthogonal polynomials. Which are those polynomials? The Hermite polynomials. And this is the whole family of Hermite polynomials. So when the interesting thing is that although these functions seem not very relevant, when you multiply these functions with a Gaussian window, what you get is what we have here, is the derivative of Gaussians. So by multiplying these polynomials with the Gaussian windows, we get a family of Gaussian derivatives, which, as I said before, are very good models of very important cells in human perception. And those are the ones we use to analyze the image. Okay, so we can build an analysis and a synthesis scheme. The analysis consists, you get the image, you convolve the image with these Gaussian derivatives. You can subsample, it's optional, you can or cannot subsample, and then you get the Hermite coefficients. And when to go back and to synthesize the original signal or image, you take the coefficients, you sample and then interpolate with functions that are also very similar to the ones you use in the analysis stage, and then you get back the original image. Okay, so a very nice thing is that there's a discrete representation. Maybe some of you know that the whole family of Gaussian derivatives can be approximated by the family of binomial functions. Binomial functions are the discrete counterpart of the continuous Gaussian derivatives, and that is very nice for discrete approximation of the transform. Okay, and there's a fast algorithm. If you're familiar with the fast Fourier transform and you remember the butterfly operations, there are butterfly operations that can be used to make a fast algorithm of the Hermite transform. So, and it's even more efficient than the FFT because there are no multiplications needed. Binomial functions can be implemented with only additions. So you can make any order of transformation with just additions and subtractions. Okay. So these little crosses are called butterflies, and you're familiar with fast Fourier transform is the same kind of thing that we use in the FFT. Okay. So how does this look in an image? We have here a medical image. It's a computer tomography image of the brain, and if you convolve this image with all these derivative of Gaussians in 2 dimensions, this is what we get. You see that 0, 0, the coefficient is just a low-pass version of the original one, but the 0, 1 and the 1, 0, as you see, is very useful to detect edges, and that's something I insist very important for human perception. And this would be the 0, 2, the 2, 0, the 1, 1 coefficient, and so on. No? All these features that we get here are features that we somehow also calculate in our visual system. Why do we know that? Because the models of our visual system can be modeled with the same operators that we use to extract these images. So this is the kind of features that we use to solve more complex problems, like recognizing a person. Something very important I'm going to talk about is that this transformation allows us to make rotation. Why do we want to make rotation? Most important features are one-dimensional. What I mean, most important features in images are edges, lines, and within a small field of analysis, those are one-dimensional features. An edge, no matter what the direction of an edge, can be analyzed very well in one dimension. Two-dimensional things, what are they? Maybe texture, and listen, noise. No, noise is a two-dimensional feature, and I'm stressing this because we're later going to see how we can reduce noise with this method. Okay. There's obviously there are three-dimensional version of the transform, so it's just the same, but it's just 3 dimensions. And I'm going to show you what we can do with this. I said that we can use it to do multi-resolution, so we can have here original image, Hermite expansion, and then from the 0 or the coefficient, I can make another expansion. And from the 0 coefficient, I can do again another expansion, and I get the so-called pyramid structures, hierarchical structures for image analysis. Okay. Examples of what we can do with this transformation. Noise reduction, very simple method to do noise reduction. Let's assume that this red light is the edge on an important object. Okay, so this is the edge of an important object. And all these blue circles are the receptive fields. of my Hermite transform. So what I can do is the following: the receptive fields that are just over the edge, I'm going to rotate them so that the principal orientation is, as you see, orthogonal or perpendicular to the edge. Yeah. So that's going to be the most important orientation of analysis. Yeah. And if I do that, I can get things like this. For instance, this is the original expansion that I showed before, and this is the rotated version. As you see, in the original expansion, we have the important features in x direction and one direction. For instance, the edges. This is the x component and the y component of edges. With this rotation, everything is in this line. This line no longer represents the horizontal direction or orientation. It represents the orientation of maximum energy. The orientation towards the principal edges are oriented. And in all the remaining coefficients, as you see, I have two-dimensional features, which are not very relevant for image perception. And when we have noise, all the noise is going to be contained in these coefficients. For instance, I think this is a noise reduction, but what is doing the noise reduction algorithm is just that, putting everything in one dimension, and everything that is two-dimensional is contained here. And with that, we can do things like this. I mean, when I just one thing, if I have a noisy image, all these coefficients can be reduced to zero. They can just be neglected. And I reconstruct the image with only the most important direction of the feature. Yeah. So I'm going to delete everything that is two-dimensional. Yeah? And by doing that, I can do things like this. This is a remote sensing image. And all this texture that you see here is noise, is inherent to the acquisition system. And when you apply this method, we get this. This is very difficult to get with standard methods, because as you see, the principal objects, for instance, this is a river, this is a landing lane for airplanes. Those lines, contours, edges are very well represented here. They are not blurred. When you try to reduce noise, normally the image gets blurred, and here it's not blurred. They are very well preserved, they are sharp, and all two-dimensional things, which is mostly noise, has been removed. No? This is one of the things that we did with this transform very successfully. We also use it to do image coding. Image coding is again the same story. We have important objects, so let's classify objects in zero-dimensional. What is zero-dimensional? Nothing happens. I have a regular surface. I have a regular piece of the image where there's no edges, there's nothing, just homogeneous region. Then I have one-dimensional things like edges, contours, and I have a two-dimensional things that can be more difficult to represent, texture, that are also important. And maybe I need more information, more coefficients to represent two-dimensional things. So what happened? Okay. This is the classification of the image. This is Lena. And when you see a red dot, it's a zero-dimensional thing, just an homogeneous region. When you see a green dot, we have relevant one-dimensional structures like edges. And when you see blue dots, it's two-dimensional. So what we do to transmit this image, well, if I'm going to transmit the red dots, I only need one coefficient, the zero coefficient. If I want to transmit the green pixels or places or dots, I need only these coefficients, which are the first dimensional. And in order to transmit the blue ones, I need all the coefficients. So I can do image compression in that place. No? Okay. We have done image fusion. So the algorithm is a bit more complex. It's a combination of coefficients from both images where I want to do image fusion. I'm not going into detail, but it's using all those properties I mentioned before. And this is an example. For instance, this is the ground truth. This is, I don't know if you noticed that this is an image where a part of the image is blurred. The central part is blurred. You notice that it's blurred. And in this one is the opposite. The central part is sharp, but the other one is blurred. So if I have these two images, which happen very often because of the acquisition way of taking the image. I have two images of the same object, but in one image, one part is blurred and the other one is and the other one is blurred in a different place. I want to combine, to fuse these images to have what I have here at the bottom, which is the ground truth. And with these methods, I can get like things like this. As you see, all these images, which are fused images using different methods. This is the Hermite transform. This is wavelets. This is another kind of wavelets, etc., etc. They provide very nice results of both images fused. And as you see, the image is sharp in all places. Okay. This is the same method applied to image fusion in medical images. This is a computed tomography image. This is a resonance, magnetic resonance image, and these are results of the fused algorithms with different methods. And in these images, you see that both information is present. I mean, the information of the computed tomography, which is mainly bone, these white parts of the brain are bones, so it's here. And what we want to rescue from the magnetic resonance image is the texture, the gray matter. The gray matter is present in these ones. So all these are results of fusion with these methods. This I like very much. This is a fusion in remote sensing. This is a panchromatic image. You know, satellites, optic satellites normally have two kinds of images. One is a panchromatic image, which is a black and white image, but with higher spatial resolution. And they have spectra bands, which in this case is red, green, and blue, but with lower spatial resolution. I think you can notice that there's more detail here than here. No? So this one has higher spatial resolution, and this one has higher spectral resolution. So colors are here, details are here. What I want to do, I want to fuse them in order to have in one single image both things. This is the result that we get. As you see, it has the spectral content, the colors, and we have here the detail of the panchromatic image. This is called pan-sharpening. It's very useful for remote sensing. And here we can see that this image, this result is much better than this, than this, than this, and this is one we obtained with Hermite transform. Okay, last but not least, optic flow estimation. What is optic flow estimation? We have video, we have a sequence of images, and I'm interested in obtaining these vectors. What are these vectors? These are motion vectors. They tell me where each part of the image is moving to, and I need to find this vector field that tells me exactly how objects are moving here. No? For instance, this is square, which is going up and down, and this is the vector field, which is going to see up and down. You see that we have problems in the boundaries of the objects. We have problems here. We have problems here. Okay, this is another way to represent motion. We have here a scene of just 2 frames of an American football game, and we have here another way to represent motion. So colors tell me what is the direction of motion. So if it's red, it's going to the right. If it's green, it's going to the left. Blue going down, and yellow up. And the intensity of the color tells me how much the motion, the amount of motion, no? Oh, sorry. So this is motion represented with this motion map. Okay. So the algorithm is complicated. I'm not going to discuss the algorithm, but it's based on Hermite coefficients. And what we use it in medical images for, this is a sequence of computed tomography images. This is the heart. This is the left part of the heart. This is the right heart part of the heart, ventricle, auricula, ventricle, auricula. I insist, left and heart. And this is the motion vector of a whole sequence of beating of the heart. And when we show this to the doctor, tells me, okay, it looks nice, but I am only interested in what happens with the left ventricle. So what we have to do is, with one of the techniques that Dr. Jimeno Alvera showed you before, we segment the ventricle, and this blue line represents the borders, the edges of the left ventricle, and if we intersect this contour with our vector fields, we get this. No? And this is more meaningful for the medical doctor because he now knows what part of the ventricle is moving right. So if there is an ischemia or a heart attack, there will be one part of the muscle that is not moving, and the arrows will be very small. And they can also check whether the beating is right according to the synchronization with the electrocardiogram, so on. And this is one of the things that we have done with this method. And I cannot, hold on, I'm still, 5 minutes? 10 minutes, okay. I couldn't leave neural networks out of this talk, right? How neural networks are, are they good models of human vision? Because now everybody, we use them. Everybody is using neural network now. So is everything that I said before is useless, or why are these so good? So the story with neural networks is that when they appear, the first models that appear were the fully connected, the fully connected networks. And when they were used to analyze image, they were useless, They didn't work. Why didn't they work? Because this model is a model of what happens in the deep layers of the human cortex. So it's like if we put an image that we received in our eyes, if it is like if we put that image in our deep cortex. It doesn't work. Why? Because in order to do important tasks, they have to go through the eye, and have to go through the retina and the early stages of human perception, human visual perception. And in those stages, as I just said, is where detection of important features of the image happens. So the mission of our system, visual system, the mission of the early stages, the first stages of the vision system, is to extract important parameters. So why these networks did not work at all? Because they are not doing that part. They were not doing that part of extracting relevant patterns. So that's why they never worked. Until what happened, better and better and better models were developed. And this is the story of how the error in an image classification task was measured in terms of time and the models. In 2011, this was the error that this network committed when doing classification task. So in this task, what happened, we have 1,000 classes with 14 million images, and the task is you present the image to the network, and the image has to tell you, this is a cat, this is a dog, this is a car, this is an airplane, yeah? This is human. We also make mistakes. We have a 5, whatever it means, 5 of error, yeah? So we also make mistakes. And this is the story of how networks were doing better, better, and better until 2015, ResNet arrives and outperforms a human in the task. Why is that? Is it because of this? Because of the algorithms? No way. They exist. I think neural networks exists like 50, 60 years ago. There's hardware. Yes, there is hardware. There's a lot of data. Yes, there's a lot of data which allows me to train these algorithms. But the reason is none of this. I mean, the reason why they work is because they included something called convolutional parts. Yeah, what is the convolution part of CNN? What are the convolutional neural networks? They have here the fully connected networks, but before they put layers of convolutions. Convolutions with what? With filters. What kind of filters? when we see the filters that we get when the network is trained, and yeah, so once we train the network and it's working well and it's classifying and it's recognizing people, and when we see what is happening, what happened with these filters, because the filters, I know if how this, I think you all know how the networks work. They are trained, and during training, these filters are adjusting automatically with training, by minimizing the error of the tasks they have to do. And when they finish, they're tuned, they're very well tuned, they work fine, and we see what the filters look like. This is the kind of filters that we have, for instance, in this AlexNet. Oops, this NF is the AlexNet. This is the kind of filters that we get. So forget about the color, just look at the great things and compare these filters that are the ones contained in the networks with the ones I showed you before, the Gabor filters and the Heimer's one. They are very similar. Yeah. So the conclusion is that when you let a system learn and the filters that are best to do image processing tasks, they arrive to the same kind of filters that we know that work well because they are the ones that we have in our visual system. No? So this is why they work. And with these models, we have done a lot of things. Just to finish my talk, just examples of what we have done. During pandemia, we built a COVID-19 diagnosis a tool which consisted of a system based of CNNs, convolutional neural networks, in this case UNets, that take an image. This is a computed tomography image in any format, and one segments the lungs, and then segments do the segmentation of the lesions of COVID-19, and the other one, this was a ResNet, would tell us what is the probability that this patient had COVID. For instance, this one says here 99% of COVID with this image. No, this is one of the things that we did with these models. It's still on the web. It's open. It's free. And later we did a computer-aided tool to help physicians detect important diseases that have to do with the right side of the heart. No, and this is something that includes many of the things that I mentioned: segmentation, optic flow estimation, and that's about it. So at the end, the message is human perception has been the basis of the working mathematical models that we use in image analysis in vision, and the ones that we use for very complicated tasks like recognizing a person is a very complicated task, but everything has to do with extracting important parameters of what we call primitives of images. No? That's the key of any successful method to do image analysis. So then, thank you very much. Thank you for your patience.
Thank you so much, Dr. Boris. I suggest everyone, if you have any questions or comments, to think about them while we answer some of the comments that have been made through the Zoom meeting. The first one would be, what do you consider to be the biggest current challenge in using vision models for computer-assisted diagnosis?
Okay, in diagnosis. Okay, one of the problems that we have in automatic diagnosis is the lack of information. No? Databases are small compared to natural images. So one of the challenges that we have is the amount of images that we need, for instance, to train a model of this. No, in order to train a neural network, you need very large databases. No? So that's one of the challenges that we have. So what people are doing is trying to find new methods for data augmentation, image generation, no, generative models to produce synthetic images simulating COVID pneumonia, which help you to enlarge the size of the database. No? And on the other side, trying to find models that need less information, less training models. No, that's the challenge in this.
Thank you for your answer. The next one would be, are there current clinical applications in Mexican hospitals that already use these vision models developed in your labs?
Yeah, well, yeah, I think more and more we are experiencing that more and more people in hospitals are using data science, artificial intelligence, computer vision methods to help diagnose. No, we're not trying to substitute the medical expert. We're just trying to help him to make a better diagnosis. And bit by bit, artificial intelligence-based models are being used in private and public hospitals to help, for instance, with data science. They look at the clinical uh, uh, data of patients and they help predict a possible disease that the person is going to be within 10 years. No, and with medical images, there are now many methods that are trying to do that are helping medicals to segment tumors, to analyze many things, because medicals radiologists have to analyze hundreds of images, and they commit mistakes, so they need automatic tools that help them do the diagnosis. Yeah, and it's happening more and more in Mexico.
Thank you so much. I think it's very interesting to see how we are not left behind in Mexico. We are actually applying these kind of technologies. And the next one would be, in your experience, how much does subjective human perception influence the quality assessment of processed medical images?
Well, that's a good question, because when you have visual perception is very important. When we buy a TV, what is important is the quality, right? You like it or not. But when you're dealing with medical images, what is important is the diagnosis is good, no? So it's a very different criterion, the one that you have to use when evaluating whether something works or not. So you need definitely an objective measure to be sure whether your system is working well or not. So you need the expert, and you need to train the system, and you need something very important. Once the system is trained and is doing results and is giving you results, if the results are good, they are not necessarily based on what's important. No? Something, for instance, one of the things that we notice is that we have a neural network and it's predicting, for instance, COVID-19, and it successfully predicts, oh, this patient has COVID-19, this one is 19, and then when you look at something that is called the heat maps, that tells you in what parts of the images the system is looking at. They are looking outside the body. They are looking at the catheter, or they are looking whether the heart is big, and when a patient has a big heart, it's because he's sick, and then he's telling you that patient is sick because other things are not necessarily the lesions, the characteristic lesion of the system. Also, that has to be with transparency of the system, has to be with something which is called interpretability. So the criterion that you need to use whether to judge whether something is working or not is very difficult, different between natural images and medical images, for instance.
Yes, it's important to have these problems very present, right? Thank you so much for your answers. And again, an applause, please, for Dr. Boris. Do you have a question? Okay.
I'm going to make an announcement while he takes the word. Next week, 4 September, we have the MEXCAS. MEXCAS is a medical image analysis conference. It's a national thing that we do for people who do image analysis in Mexico, and we'll have this conference for September in the School of Engineering. So more information with that, please.
First of all, thank you for your presentation. I have a question. If we already know which filters work, because earlier you showed us the Hermit filters and the street filters that can obtain a lot of information about the images. So then why we need neural networks, I mean the convolutional networks to extract those filters if we already know them? So why we need them?
That's an excellent question. That's an excellent question. This is the point. If we know that after tuning, the filters that you're going to get in the first layers of the network are already known, no? Because they are like Hermite or Gabor-like functions. Why do we need to train the network? That's an excellent question. No? So what we do is that we don't train anymore the whole network. We take a neural network that has been pre-trained with standard images, yeah, and because we already know that the first layers are going to use these filters. No, we're going to find out these filters, and we only train the last layers because the last layers have to do with the specific task that you're doing, specialized in the kind of images. For instance, if you're using medical images, you train, you do that's called fine tuning. So you fine tune the last layers of the image because they are very synchronized with the kind of images that you are using in the specific task. If you are using the network to detect other kind of images, then you find the network with this set of special images. Yeah, because as you said, it's very well proved. The first layers will have the same kind of filters because it doesn't matter what kind of image you're looking at, you're always extracting the same kind of information, edges, line, etc. But when you start doing more complex functions like recognizing a person, you start looking at details, no? Whether a person has hair, lenses, or whatever, and then the last layers specialize in those details, no? Okay? Thank you.
Thanks.
Okay, I think that would be everything right now. Can we please give an applause to Dr. Boris, please?